Hello, my name is Charles Makel from Argonne National Laboratory, and I'm going to give a presentation here on some of the work that I've been doing with agent-based modeling using the Wolfram Language and Mathematica. Basically, agent-based modeling is a technique for modeling and simulation that has gained widespread popularity and use in the last 20 years, probably 25 years now. The methods of agent-based modeling are able to uniquely address modeling heterogeneous populations of agents at an individual level. So in terms of the outline of my talk, first I'll say a few words about what agent-based modeling is. I'll talk about the essential components of every agent-based model, talk about agents, some simulation constructs and agent interactions and the environment, which are components of agent-based models. I'm going to show some work that I did with modeling COVID-19 for Chicago that gained a lot of attention at the time. And it's a wonderful application of agent-based modeling in general for any kind of epidemiological modeling, because there's a lot of interest in the heterogeneity of people and groups in the population now than there's ever been. Okay, what is agent-based modeling? Well, there are many definitions, of course, but this is one that really captures the main idea. It's a modeling technique for representing a population of entities which we refer to as agents. Agents could be people. We often model people as agents. Could be any other kind of entity, though, that has what I would call behaviors. And that interaction with other agents in a repeated way is important. Agent-based modeling goes by many other names. For those of you not totally familiar with agent-based modeling, for example, individual-based modeling, there's whole conferences on IBM models. There's certainly other conferences on multi-agent system models. For all practical purposes, these things are the same as agent-based models. You know, there's no point in really cutting it too carefully. It's not really meaningful. Now, interestingly, ABM theory is, agent-based modeling theory, methods, and applications come from many disciplines, including complexity science, social sciences such as sociology, political science, ecology in general. The field of ecology really looked at populations of individual species, let's say, or individuals within a species, and food webs and you know, within ecosystems, and they coined the term IBM. In addition, the fields of systems and industrial engineering, that's where I come from. You know, and we do a lot of simulation science in that field and traditionally have. Computer science is getting involved with particularly multi-agent systems. And then most recently, there's things in computer gaming, things like agentics seems to be a new term. So there's just a lot of disciplines, a lot of people speaking different kind of languages to some extent about the same thing. And moreover, it's a very interdisciplinary field. So there's no general, you know, agreed upon definitions of a lot of things in agent-based, but this comes back to what I would call my research program and interest in agent-based modeling. I build large-scale, real-world agent-based models specifically for the purpose of informing decision makers by answering the key questions they might have. And, you know, I've done this for a variety of fields. I mentioned epidemiological modeling, I'm also engaged right now in large-scale applications of ABM having to do with, let's say, how misinformation, spreads, across social media platforms, and how that information could influence people, things like that. And also another application where I'm looking at climate change models and forecasts or projections of how temperature, humidity, environmental factors could change in the future, and what those effects could be on individuals in the population in particular. So it's a good application. The latter part, effects on population, for agent-based modeling, because different people will react differently. One of the things that I've noticed, and I've written a lot of papers on agent-based modeling and tutorials, and I'm currently a co-editor-in-chief of one of the journals, Journal Simulation, focusing on agent-based modeling. But I've noticed that agent-based modeling has been stymied as a field because it's simply too complicated. It's too hard to understand. It's too hard to understand how to do it. And it's just too hard to do it. So my goal is to make agent-based modeling simple. And of course, I've been on this goal for a year where I've been doing research on trying to find and identify the simplest agent-based model. From that, one could add layers of complexity to agent-based modeling, kind of building it up from the ground up. And when I say simple ABM, I really mean both simple agent-based modeling design, how we think of designing agent-based models in a simple way, and have simple representations of agent-based models to communicate to others. But also, of course, which is kind of the subject of this talk, simple agent-based modeling implementation. There's many agent-based modeling toolkits that are out there. One could, grab one of those. We actually have developed one ourselves here at Argonne called Repast, but there are others called, popular ones, NetLogo. Mesa is kind of a Python version. So, but the toolkits themselves require you to learn how the toolkit works in a whole language of the toolkit. So one of the things I'm trying to do is identify how people could actually implement agent-based models in some native computer language, and see how far we can get with that, and if that's still too hard to do. Anyway, that's where the Wolfram language comes in, and I've been working on Wolfram for several years. Now here I'm just showing you something I did in the Wolfram language, just to illustrate the kind of things we're talking about agent-based models, right? So so sometimes with agent-based models, and especially large-scale ones, we begin with creating a synthetic population of agents. And that would be kind of, in this example, we've developed a synthetic population of the 2.7 million people that live in Chicago. So we have basically 2.7 million agent expressions, so to speak, in the language, based on inputting all kinds of census data